Hello, and welcome to the Unit 5 Supplemental lesson. This is Synthetic Division Extended. So if you watched Lesson 5.2, I believe, where we talked about polynomial long division and synthetic division, when we discussed synthetic division and talked about what's known as Ruffini's rule, we only used it for monic linear polynomials, meaning, you see this right here, monic linear polynomials. And what a monic linear polynomial is you can see it right here, is x minus a, or x minus r, whatever, right? It's the idea of monic is a coefficient 1, a leading coefficient of 1, and then the degree of x is 1. So it's just 1x minus something, right? And those are called monic linear polynomials. And this is the only case that is typically taught with synthetic division. It's pretty standard in the United States, right? That this is all teachers teach you, is that, oh, you can only use it with linear factors if the leading coefficient is 1, right? That's not true. That's actually not true. Yes, that's Ruffini's rule. That's the typical one that's taught, but it actually does not matter. There is an extension of synthetic division that works pretty much the same, just a few tweaks. And so we're going to talk about how to do that in this video. And that way, you can use synthetic division for any polynomial. So first, I'm going to just do this review problem just as a recap, just so you can remember how does synthetic division work, right? Well, the idea is I'm going to take the coefficients of my dividend polynomial, the numerator up here, right, the thing I'm dividing. And so I'll say, okay, let's look at the coefficients. Keep in mind, you must do it in decreasing degree order, right? Power of 4, then 3, then 2, then 1, then 0, right? So 4, 3, there's a 1 and there's the 0. I don't have x to the 2, so that means that's 0x squared. So when I write out the coefficients, I've got 1x to the 4th minus 3x cubed plus 0x squared, which you don't see in the polynomial, plus 27x minus 81. So those are the coefficients of my dividend polynomial. And then typically, at least the way I've been taught, is to put the root of the denominator into a box. Meaning, if you look at x minus 3, set that equal to 0, the root of that is 3, right? So x equals 3 is the root I'm sort of testing. When I extend synthetic division, I'm going to kind of stop using this box. It's still going to have some numbers on the left side here, but you'll see, okay? So anyway, I'm going to draw my line here, and I multiply, add, right? So the process of synthetic division is you first drop the leading coefficient, 1, down here. And as a review, the process is take the numbers that come down here, multiply it by the root that's in this box, place it beneath, and then add. So what I'm going to do is 1 times 3 is 3, and negative 3 plus 3 is 0. And the next thing I'm going to do is 0 times 3, that's 0. And 0 plus 0 is 0. Get rid of that. There we go. 0 times 3 is 0, right? So I'm doing 0 times 3 is 0. And 27 plus that is 27. And then 27 times 3 happens to be 81. And negative 81 plus 81 is 0. And to interpret this result, right, this last column, this is the remainder. And what's over here is your polynomial, right? And so you have, this is x to the 0, this is x to the 1, x squared, then x cubed. And you just go from right to left, starting at the degree of 0 and then increasing by 1 every time, right? And so I see, okay, I have nothing left over. And so I have 1x cubed plus 27. And notice it says give the complete factorization of the polynomial. And so if you remember, this is x cubed plus 27. That's x cubed plus 3 cubed, squared, 3 cubed. This is a sum of cubes identity, which I've told you in class you have to memorize that, right? So this factors as x plus 3 times x squared minus 3x plus 9. And if you're not sure where in the world I came up with that, go review the first video on factoring techniques and look for something called sum or difference of cubes, okay? That's not really the topic of this video, but that's the full factorization of that. And so if you ask, what's the complete factorization of this polynomial? Well, it's x minus 3, right? So the complete factorization is x minus 3 times this quotient polynomial. So x plus 3, x squared minus 3x plus 9. What's interesting here is you'll see that this actually makes a difference of squares identity, and this is actually the sum of cubes identity. Which is kind of interesting, right? But it's not both, it's one or the other. It just kind of happens with this polynomial. Anyway, that's just a review, right? Review of how to do synthetic division with a monic linear factor and interpreting the remainder and then completely factoring from there. So now on to the new stuff. So what we're going to talk about is three things in here. Non-monic linear divisors, meaning it's this thing right here. It says kx minus a, where k is not 1. So, like if I had 3x plus 1, right? It's linear because the power is 1, but it's not monic because the leading coefficient is 3 and not 1. So first we're going to talk about that. Then we'll talk about monic nonlinear, meaning the leading coefficient is 1, but the degree might be like x squared or like 1x cubed or something like that, right? And then on the last piece of the video, we're talking about neither. So it could be like 3x squared as your leading coefficient, right? So the degree's not 1 and the leading coefficient isn't 1. And so we're going to put all three of those, all three of these things together. So here's how this works. There's kind of two ways to do this. You could use the root of kx minus a. So like if you're looking at example 1 down here, you have 3x minus 4. And if you find the root of that, add 4 to both sides, you get x is 4 over 3. You could set up synthetic division with 4/3, but you'll have to be careful with that because if you do that, if you use synthetic division of 4/3, the factor you're testing or dividing by is actually x minus 4/3 and not 3x minus 4. You see, this and this actually have the same root, but they're technically not the same polynomial, right? So I would be careful with that. You can still do it and manipulate it in such a way that it's successful, but I'm actually going to do it a bit of a different way, all right? And so what I'm going to do is I'm going to look at the negation of a, which is kind of what you do in regular here. I told you earlier that it's the root of this polynomial, and it is. But really, you can just think of, if you have minus 3 here, the opposite of that is plus 3. And so that's what I mean by the negation of a. So you're just going to look at that minus a or plus a, whatever it is, right? And just flip the sign on that, okay? And so here, let me model example 1 here for you, okay? And this is, honestly, I probably should have just taught you this one in the first place, but hey, whatever, right? Who cares? You're watching this video and you're learning it now, yay! So I see that it's 3x minus 4. If this is kx minus a, then 4 is a. So I'm going to flip the sign on that and make a 4. So the thing I'm going to put in the box is 4, kind of just the way you normally do it, right? And then set up my coefficients. So I've got 6x cubed minus 5x squared minus 7x plus 4, right? And I'm going to do synthetic division the same way. But what I like to do, and this is where I'm going to change it a little bit, I'm going to draw this because this is how, when I do extended synthetic division, I like to draw it this way instead, okay? It's kind of like I made the box really big. And so 4 is still up here. And it's a similar process, but what you have to do is this leading coefficient 3, when I do synthetic division normally and I get these numbers here, I'm going to divide those numbers by 3. And so let me show you how this works. So the first step's the same. You drop the 6, okay? But you're not going to do 6 times 4. You're not going to do 6 times 4 and then put that here. You're going to divide 6 by 3 to get 2. And so once you have that, then you take 2 times 4 to put 8. So I got -5 plus 8, and that's 3. But again, I'm not going to do 3 times 4. I'm going to divide 3 by 3. Or I'm going to take this number and cut it by 3. So that becomes 1. And then I do 1 times 4, which gets me 4 here. -7 plus 4 is -3. Divide by positive 3 is -1. Repeat. -1 times positive 4 is -4. -4 plus -4 is 0. Now, and this example doesn't have a remainder, so it doesn't really work. But when you do synthetic division this way and you have this division by the lead coefficient, whatever remainder you do get here, you do not divide that by 3. So don't divide that. So I'm not going to do 0 divided by 3 is 0. I'm just going to leave that as is. And so this is my kind of separator. This is the remainder. And then the bottom terms are the coefficients. So that this is x to the 0, x to the 1, x squared. So you see I have remainder 0 means the quotient of this is 2x squared plus x minus 1. And that's it. Done. That's how you do synthetic division for not monic linear factors. Okay? Let's look at one with the remainder. Okay? And I'm going to switch to blue here just for fun. I like to switch up the colors. So again, I take the negation of a, which is that the constant, right? The constant at the very end is 1. So I'm going to flip the sign on that. It's going to get -1. So I got -1 here. And I'm kind of extending this box kind of like this. You'll see why I do this, especially as we go on. I do 24x cubed plus 2x squared minus 27x plus 10. And the lead coefficient is 2, so I'm going to divide by 2 over here. So, same process. I drop the 24, get 24 here. I guess I didn't need that much space, but whatever. 24 divided by 2 is 12. 12 times -1 is -12. I don't like the way I drew that negative. It's too fat. I say sorry. 2 plus -12 is -10. Divide -10 by 2 is -5. -5 times -1 is +5. -27 plus 5 is -22. 22. To cut that in half, it's -11. And -11 times -1 is +11. 10 plus 11 is 21. And I'll draw my bar kind of here so you can really see. And you'll really see why I'm drawing this bar here, whereas I used to not, right? So yeah. So this is the remainder. You do not cut that in half, all right? So that's my remainder. This is my x to the 0, x to the 1, x squared. So the quotient polynomial, well, it's not a polynomial. The quotient of this expression is 12x squared minus 5x minus 11. The remainder is 21. You do not cut that in half. Plus 21 over the thing you were dividing by, which is 2x plus 1. And there you have it. So that's how to do synthetic division when it's not monic. Yeah, pretty simple, I think. Not too hard to follow. It's the same thing. You just kind of cut it. You divide it by the lead coefficient, and you're good. Okay. Now let's bump it up a notch. Next, we're going to do synthetic division of monic nonlinear divisors, meaning 1x squared plus blah, 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 or 1x cubed plus blah, 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 right? And so you can see all this mathematical jargon I've put up here. It's a polynomial where the leading coefficient is 1. That's it, okay? That's what we're concerned with. Now, this is where it gets a tad different, a little more complicated, but relatively the same process. So the same way you negate the sign of the constant, right? Back here, right? You take 4, you flip the sign, you make it -4, right? Sorry, you take -4, you flip the sign, you make it +4. Down here, you took positive 1, you flip the sign, you make a negative 1. What you're going to do with terms that have more than 1 is you're going to flip the signs of all coefficients, but ignore the lead coefficient, okay? And then you're going to set up a sort of diagonal of the coefficients of the divisor out to the side of the box, okay? It is better to just see this in progress than for me to just explain, okay? So a similar setup. First, the dividend, right? It is 1x to the 5th minus 1x fourth minus 7x cubed plus 3x squared, 4x, negative 12. So that part's the same. Actually, I'm gonna lasso this and move it over a little bit because I don't need to be stingy with space. Okay. You know what? I'm going to move that over even more. I told you I don't need to be stingy with space. Let's use up some space here. Now, the divisor, right? It's x cubed plus 0x squared minus x plus 2. You're going to take all the coefficients. You're going to ignore, I'm going to say ignore this, ignore. And you're going to set up the opposites of all the other coefficients. So the opposite of 0 is 0. The opposite of negative 1 is positive 1. And the opposite of 2 is negative 2. So when I draw this box now, so I'm going to drop this down here. And this is where you're going to need some space. You're going to make this. What you do now is you make an upwards diagonal of those 3 constant terms. 0, 1, negative 2. Okay? And here we go. So here's how this works. See, it's getting a little bit more complicated. You drop the 1, like so. And now what you're going to do is you're going to repeat this diagonal motion throughout. All right? It's going to sort of diagonally go across every time you do this. So you're going to take 1 and you're going to multiply it by 0. And we're going to put that in the next column at the bottom. So 1 times 0 is 0. Next you're going to do 1 times 1. And you're going, again, you got to keep this diagonal motion. If it helps, sometimes you can misalign this. If it helps, you can put some separators here to really see it. I'm not going to because I don't want all of that on the screen right now. But you can, okay? 1 times 1 is 1, and then 1 times negative 2, right, now I'm doing the last one. 1 times negative 2 is negative 2. Now, don't add everything. Go to the next column and add. Negative 1 plus 0 is negative 1. Repeat, and you're going to keep that diagonal motion, but now instead of being here, you're going to go diagonally this way, right? So it's negative 1 times 0 is 0. Then it's negative 1 times 1 is negative 1. And then it's negative 1 times negative 2 is positive 2, which puts it here. Move to the next column. Negative 7 plus 1 is negative 6. Repeat. And you're just going to keep repeating this, right? Negative 6 times 0 is 0. Negative 6 times 1 is negative 6. And negative 6 times negative 2 is positive 12. And then add, right? But I want you to notice when you add this next column, right? If I were to repeat this, if I were to do it again, right? I add all these up together, I get 0, and then I do 0 times blah, blah, blah. This would create, this will be a 0, and if I multiply 0 by all those 3 things, I get 0, 0, 0. But I didn't have a coefficient here, right? So that means you stop. If this diagonal bleeds into an empty space, that means you're done and you don't actually make that diagonal there. And so for the rest of the terms, you just add. So from here, 3 minus 2 minus 1 is 0. 4 plus 2 is 6, minus 6 is 0. And 12 minus 12 is also 0. And now this is where it gets, this is where you got to still be more careful. This is no longer the remainder. It's a tad different. I mean, it's part of the remainder. But when you divide by these things, when you just divided by a linear, the only remainder you could ever have was a constant. But now that you're dividing by higher degree polynomials, you can have a remainder that it itself is a polynomial. So here's how you kind of determine what's the remainder and what's not. However many numbers were in this diagonal, in case 1, 2, 3, right? That is where this splits, meaning start on the right, all three of these are remainders, okay? So you split this down the middle. Now this remainder is a constant remainder. And this remainder is an x to the 1, and this remainder is an x squared. So it means remaining, you have nothing. Right? It's all zeros. So there is a 0 remainder. On the other side, it's our typical x to the 0, x to the 1, x squared. So with no remainder, I have x squared minus x minus 6. And that tells me that that cubic polynomial was in fact a divisor of this. It divided evenly, and this was the quotient. Okay? That was a little bit more complicated, right? But still relatively the same process. It's just that you start having this diagonal motion, right? And maybe the tricky part is understanding what's your remainder, yeah? Again, if you only had 2, then I would have put the bar here, and it just would have been those 2, okay? So let's see, to really see this remainder piece in action, we're going to move on to the next example. So let's set up my coefficients. 2x cubed, 9x squared, 3x negative 14. This one's a little bit smaller, not as long. And I'm going to look at x squared plus x minus 2. Now, again, ignore, right? You know what? Let's put that in red. It's funny because I'm putting an x here. That's better. Ignore. Okay. The coefficient on 1x, right? Flip the sign. That's negative 1. Let's flip the sign here. It's 2. So, draw my little thing here. Draw a straight line. Draw it like this. My diagonal starts as negative 1 and then 2. So I'm going to repeat the process just like we've been doing. Drop the 2. 2 times negative 1 is negative 2. 2 times 2 is 4. Again, what I did was 2 times negative 1 is negative 2. 2 times 2 is 4 to create that diagonal motion, and then I would do it again, right? So 9 minus 2 is 7. 7 times negative 1 is negative 7. 7 times 2 is 14. Okay. Now notice, if I add this again, I get something here, right? I get whatever this number is. If I repeat it, I'm going to bleed into nothing, right? There's nothing out here. So I'm done, right? I just add now. 3 plus 4 is 7. 7 minus 7 is 0. Negative 14 plus 14 is 0. Okay? And so, again, I guess I was wrong. I guess I was mistaken. I think example 3 and 4 represent no remainder. Example 5 will show us one with remainders. Okay? But again, because I only have 2 things here, 1, 2, that means I split it like this, okay? That's the remainder constant. That's the linear remainder. And then this is x to the 0 and x to the 1. So what I have is 2x plus 7. That is what I'm left with, okay? All right. I guess it's not true that you see example 4. So let me, you know what? Let me cross that out. See example 5. Haha. Because I thought it was 4, but it's really just 5. Okay? And that's it. Let me make that, sorry, well, where'd my 7? 7. Sorry, I just like them to be perfect rectangles. Okay, that's that. Okay? And always, you can always double check. If you look at the lead degrees, or well, not the leading, I mean, they are the lead, but right, the degree here was 5, the degree here was 3. That means your quotient should be of degree 2, right? You take the highest degrees. That should be what the leading term looks like. I had x cubed, I divided by x squared. The leading is 2x, okay? All right. Example 5 will show us how to deal with no remainder, okay? So let's start with this first one here. Be careful with your powers now. Notice this is degree 5. There is no x to the 4th. There is no x to the 1. So it's 1x to the 5th, 0x to the 4th, 2x cubed, negative 8x squared, 0x, negative 16. And for, if I had a look at x squared minus 3, well, I guess I don't know where to put this. Let's just put here, x squared minus 3, that's x squared plus 0x minus 3. So we're going to be doing 0 in 3, right? Because you ignore that first one, right? Ignore. So 0, 3 is this diagonal. It's fine because you don't have that middle x, so it's just a coefficient of 0. So drop the 1 and we do the process. I'm just going to show you how this works. 1 times 0 is 0, 1 times 3 is 3, 0 plus 0 is 0, 0 times 0 is 0, 0 times 3 is 0, 2 plus 3 is 5, 5 times 0 is 0, 5 times 3 is 15, negative 8 plus all that, right? That's negative 8. Negative 8 times 0 is 0. Negative 8 times 3 is 24. Notice if I did it one more time, the next diagonal would be, I wouldn't have this. So I'm done. I just add. So 0 plus 15 plus 0 is 15. Negative 16 plus 24 is 8. Now, this is your remainder constant. This is your remainder linear. This is a constant. This is linear. This is x squared. And this is x cubed. So the resulting expression is x cubed plus 0x squared plus 5x minus 8 plus, and now the numerator of this thing, right, is 15x plus 8. So it's a little bit more complicated of a remainder than what we're used to. But I'm dividing that by x squared minus 3 because it didn't go in evenly. Right? And that is it. Oh, why is that a trapezoid? Oh, be a rectangle, please. Rectangle. Okay, there we go. Happy. Okay. And that's it. Yeah? We're going to do it one more time, just so you get, I just want you to have plenty of examples, I honestly, you've probably got it at this point, but the more examples, the better, right? So that you really see how this works out. Now, when you do x cubed plus 2, keep in mind that's x cubed plus 0x squared plus 0x plus 2, means you're going to do 0, 0, negative 2, right? And this we ignore. So again, 1x to the 5th, 0x to the 4th, 2x cubed, negative 8x squared, 0x, negative 16. Those are my coefficients. Create this. Now I've got a triple diagonal here, right? 0, 0, negative 2. Drop the 1. Here's the 1. 1 times 0 is 0. 1 times 0 is 0. 1 times negative 2 is negative 2. Add the zeros, I get 0. 0 times 0 is 0. 0 times 0 is 0. 0 times negative 2 is 0. That's nice, right? Multiplication of 0 is very easy. 2 plus 0 is 2. 2 times 0 is 0. 2 times 0 is 0. 2 times negative 2 is negative 4. And let's see, if I add these things, and I did again 1, 2, 3, I'd be out in that empty space. I'm done. So this ends. And I've got negative 8 plus 2 is negative 10, then 0, then negative 20. Okay? Now that's your remainder constant. This is your remainder linear. This is your remainder quadratic. And then this is x0, x to the 1, x squared. So the result is 1x squared plus 2. And now notice how this is, I guess it's just plus negative 10 minus, negative 10x squared minus 20 over x cubed plus 2. And that is it. I knew it was going to make a trapezoid. I've got to draw better rectangles. There we go. Okay. And that's how you interpret these, right? Whenever you have this remainder, the degree that's in the numerator is always going to be at most 1 less than the degree of the denominator. Okay? It could be even more less, right? I could have x plus 2 over x cubed plus 2. But what I'm saying is this will never equal this or be more. It'll always be 1 or less. I'm sorry. It'll be 1 less or less than that, if that makes sense. Yeah? And again, I put this in the denominator for the same reason I always do. It's because I'm dividing by this. And this is my remainder. And remember, 1, 2, 3 means these 3 are the remainders. Okay. And that's pretty much it. You could honestly probably stop the lesson video at this point, but we got to put both these methods together. And this is where, it's a lot. It is a lot. But it's just both things I've told you at once now, all right? So we've got 3 more examples here, but there's not a whole lot more to explain. It's just me modeling it. It's the same 2 techniques of setting up these diagonals, but now, because the leading coefficient's not 1, you got to do this divide by the lead coefficient business. So here's example 6, okay? First, as always, start out with the coefficients, 12, 12, negative 5, negative 8, negative 2, okay? And look what I'm dividing by. It's 3x squared plus 0x minus 2. Ignore. This is 0. Flip the sign. This is 2. So when you set this up, this is where I need some more space vertically, like so. I have 0, 2 in my diagonal, but because the leading coefficient is 3, I've got to divide by 3 down here. So here's how it works. Drop the 12. Here's the 12. Now divide 12 by 3. That's 4. Take 4 times 0 times 2. Do it diagonally. 4 times 0 is 0. 4 times 2 is 8. 12 plus 0 is 12. Divided by 3 again is 4. Repeat. 4 times 0 is 0. 4 times 2 is 8. Add, negative 5 plus 8 is 3. 3 divided by 3 is 1. 1 times 0 is 0. 1 times 2 is 2. If I did it one more time, I'd go out into that empty space, so I'm done, right? Also, because there's 2 here, that means it's going to end at 2, right? The remainder is going to be here. So I split this up between remainders and non-remainders, right? Negative 8 plus 8 is 0. Negative 2 plus 2 is 0. And just like we don't divide, whatever these remainders are, you don't divide by 3. That's it. That's the remainder of the constant. That's the linear remainder. This is the constant, linear, quadratic. And so what I'm left with is 4x squared plus x plus 1. Sorry, 4x. Missed that. Plus 4x plus 1. And this was an example of dividing evenly. So it's just both things put together, right? Let's see some more examples. Example 7. So copy down the coefficients. 8x to the 5th, 0x to the 4th, 0x cubed, 3x squared, 2x, 1. Right? Notice there's no x to the 4th or x cubed there. This is 2x cubed minus 1x squared plus 1. So this is going to be 2x cubed minus x squared plus 0x plus 1. Ignore 1, 0, negative 1. Flip the signs of all those coefficients. And then I'm going to divide by 2. Awesome. Oh, this is so much fun. It actually is kind of fun, I think, personally. Straight line. Okay. 1, 0, negative 1. And I'm going to be dividing by the lead coefficient in the denominator, which is 2. Drop the 8. 8 divided by 2 is 4. 4 times 1, right? Again, 4 times this diagonal will go here. 4 times 1 is 4. 4 times 0 is 0. 4 times negative 1 is negative 4. Add. 0 plus 4 is 4. 4 to cut in half is 2. 2 times 1 is 2. 2 times 0 is 0. 2 times negative 1 is negative 2. Add. 0 plus 2 is 2. Divide by 2 is 1. 1 times 1 is 1. 1 times 0 is 0. 1 times negative 1 is negative 1. And since this is 3, you know this is separated by 3. And if I did it one more time, I do 1, 2, 3, that would be bad. So I just add at this point. I know it's just over. I'm like a broken record. 3 minus 4 plus 1. Well, that's 0. 2 minus 2, 0. 1 minus 1, 0. So I'm left with, this x to 0, x to the 1, x squared. I'm left with 4x squared plus 2x plus 1. There you go. And again, see how it's x to the 5th divided by x cubed? It makes sense that that's x squared. Okay. I think example 8 should show us a remainder. I hope so. I mean, I made up all these problems, right? I just made them up. So here we go. Let's set up the coefficients. 4, no x squared, 0, negative 2x, 1. Draw this bar like so. If you look at 2x squared plus 3x minus 1, we ignore this, flip the signs, negative 3, positive 1. And that's it. So negative 3, positive 1. But the lead coefficient is 2. We're going to divide by 2. Drop the 4. 4, cut in half is 2. 2 times negative 3 is negative 6. 2 times 1 is 2. Add. Negative 6. Cutting that in half is negative 3. Negative 3 times negative 3 is positive 9. Negative 3 times 1 is negative 3. And notice if I did it one more time, I'd get over here. So because this is 2, I have my 2 remainders here. So I drop this as a bar to separate. And now I just add. Negative 2 plus 2 is 0, plus 9 is 9. 1 minus 3 is negative 2. And so to interpret this, this is the constant remainder. This is the linear remainder. And then this is the constant, and this is the linear. So the ending expression is 2x minus 3 plus 9x minus 2 over what you're dividing by, 2x squared plus 3x minus 1. And there you have it. That's it. That is how to do synthetic division no matter what. And even though there's a little bit more steps, even though it's a little more complicated with, you have to do these diagonal rows and you have to make sure you divide by the lead coefficient, I still think this is preferable to long division, right? Long division is, you have that idea of misaligning your variables and stuff like that. The only thing that would really make this tricky, I think, is knowing when to stop and interpreting that remainder, and being sure you set up all the coefficients correctly. Like here, students might be tempted to say 8, 3, 2, 1 rather than 8, 0, 0, 3, 2, 1. Yeah? So careful of that. But as long as you know that and you know what you're doing, there it is. And so, yeah, this is the supplemental lesson. For my class, I am offering extra credit. Of course, I'm not going over these problems. These are for you, but there are some extra credit problems here, doing plus 5 points on your exam. A few of them just to go walk, right? Non-monic linear, monic quadratic, non-monic nonlinear. Yeah. And then there's also this fun challenge problem, which really would show your mastery of this unit. So honestly, if you're able to do this mastery problem, you're probably going to get 100 on that test. You probably don't even need that extra credit, but hey, it's there if in case you want to try it, okay? And there you go. If you have any questions, come see me in class. I'm happy to talk about this in person with you, and I hope you have a wonderful day. I hope you enjoyed this video, and have a great day.